Hello guys, let's start. Okay, thank you so much. Hello everyone, we are the team Madaxis from Spyropoulos Studio. This year, our studio brief focuses on Elemental 3.0, Phenomenon as Technology, where our objective was to look for phenomenon in nature and explore how these natural occurrences can be implemented in architecture for potential paradigm shift. Our project focused on phenomenon of line that can be found in nature as an automated process of constructing spaces. Our initial exploration uncovered the interesting process of silkworm depositing lines in nature, which highlighted the line's behavior properties, elasticity, and multimateriality. Moreover, we observed how the lines, guided by collective behavior of silkworm, can evolve into a lightweight infrastructure for the silkworms to crawl around its environment. This presented as a compelling phenomenon of using lines to construct infrastructure. As a part of our case study, we looked into works of Saraceno, Newman for Use, and Ioakim, who conducted research on making line architecture. These researchers translated a natural occurrence into a spatial experience, allowing users to navigate within the structure akin to the movements of silkworm. During this study, we found a gap in the research based on line placement, which was the need for scaffolding. One example of line deposition project, which is also automated, is ICD 2014 Pavilion, where they used the inflatable as scaffolding in order to deposit the lines, which is radically different logic from depositing lines directly in space without any active scaffold. Therefore, our project looks into how we can use line architecture by an automated process of line deposition as a prototypical system that would fabricate lightweight, elevated, and translucent structures. We as a team see line both as elemental and technological way of constructing new spaces. And in a larger city context, a line as a concept of connection creates new opportunity by connecting different parts of the city at multi-levels, by providing a space for people to interact, at the same time allowing the people to experience the city in a different manner. Our research begins by researching into the process of cocoon formation from silkworm, which relies on its body capabilities. They utilize their own body as a measuring tool to measure their immediate surroundings, collect the data of the environment as a point cloud. Afterwards, they employ their bodies to spin their intricate cocoon. Our thesis methodology starts with understanding line as a phenomenon by studying the silkworm and line as a particle spring system. Through careful observation of spinning process of silkworm, we understood a specific logic. First, the silkworm selects the anchor points from its environment to create a scaffold structure. Secondly, it constructs an infill layer. Finally, it spins an enclosed cocoon that creates the void former. This concept of continuous line deposition by silkworm gives rise to a suspended volume within its environment. Therefore, as a time-based development, the following cocoons draw support from the previous one and gradually develop an interconnected infrastructure. As a time-based aggregation of cocoon proved us how a line as an elemental way of constructing volume can result in a complex interconnected infrastructure that is lightweight. As the number of silkworm increases, the cocoon starts to layer on top of each other, creating a multi-layered, fuzzy space that floats, enabling the cocoon to be suspended with the support of sticky lines that is anchored to the environment. The recorded time-lapse of the experiment showed how the infrastructure is adaptive and grows cohesively together. By zooming into the constituent lines of the cocoon, we observed how the lines are divided into segments and how those segments have spring behavior. As the diagram shows, points on the line look for the closest points within a search radius, and when they do find the closest point, they self-organize, clump together to create this sticky, elastic behavior.
One of the properties of the line that we are interested in is the elasticity of material. This property determines the line's organization and structural integrity. To experiment with it, we first employed an analog physical form-finding spring system to understand the behavior of a network formed by elastic springs. The benefit of working with springs is the easy visualization of the axial stress and forces applied on the line. And through a gradual gradual modular addition of springs and anchor points, we explored the spatial and formal development of the structure according to the internal and external forces acting on it. This elastic behavior was then translated into a digital physics-based spring system. It was explored in a one continuous deposition of the lines spanning between the main anchor points. It also takes into account another aspect of the line we're interested in, which is the stickiness. This sets the foundation for later material and printing experiments to find a methodology that would allow us to achieve the line network through an optimum use and choice of materials. As a further exploration, we experimented with sticky materials such as cling film and tape, which gave us the opportunity to develop the line into a volumetric study to construct spaces.
So after studying one line as phenomenon, we went into interface with environment. The first iteration was carried out on second floor, AADRL, which is a rectangular space among 4 columns. Here shows the basic logic of line cohesion in space, that we first draw the outline of the space defined by the structural parts, and as we keep adding tapes to wrap the outline, it shrinks to the tube-shaped volume. And with only 15 rows, the very lightweight structure was strong enough to hold an adult inside. The second iteration we did in Bedford Square tested the line behavior in a more complex environment. Here, trees connected to form a triangular space with a void in the middle. As the volume shrinks very rapidly, we learn to control the ratio between distance and height. And with huge deformation, we see the least amount of material needed. The third iteration we did in Regent's Park, this time after finishing the triangular volume shaped by the trees, we tried to have an extension volume by picking another tree and the volume already constructed to anchor. As a time-based process, it shows the tension and the deformation of the elastic volume.
For our last iteration, we tended to scale up our structure even more in order to face the challenges of scale. We found the AA terrace to be a suitable space for this, as it is an open space that is surrounded by high and low anchoring points, like the railings, columns, stairs, etc. By scanning the environment as silkworm does, we collected the point cloud, and we used that data to generate multiple iterations based on different anchoring positions. After picking the last iteration, we started constructing the intervention. We faced some challenges taking the tape from one side of the terrace to the other. Therefore, during the first day, we applied the principal structural lines, and then the second day, we spent on wrapping those principal lines in order to have a tensed and enclosed structure. The construction of the intervention consists of 100 tapes in total. While the experiment was successful, we can notice that the top left of the structure is not enclosed due to the constraints of the human scale. Ultimately, we have successfully achieved our experimental goal, which centered around creating a translucent, floating, and lightweight structure using a continuous line. The design provided a space for students and staff of the AA to engage with and experience its translucency and lightness.
As a next stage, we see our phenomenon as a closed-loop system that is both prototypical and adaptive. This generative agent-based system starts by scanning the context, which then generates the goal lines based on detour and proxy surface logic, and which then is translated as a line placement strategy for the printer. To start, a lightweight LiDAR donor can be used to scan the urban environment with a higher resolution. That does multi-level scanning at different angles to create high-fidelity point cloud of the context that acts as a digital twin for the system to operate on. As a scanning exercise, we scanned the street around the corner, used a handheld LiDAR scanner that recorded the video to train the computer vision to look for columns, slabs, and steel structures that can take tensile force. Using this experiment, we developed a workflow to process the scan mesh into a point cloud that will help finding potential anchor points. As a method of transferring this information, we developed a proxy tube that carries both contextual and structural information onto the agents. By by incorporating the proxy tube to the setup, a structural analysis was run using the support location and potential load to get the stress displacement maps, stress vectors, and stress lines that will add up to give a structural probability map for the agents to generate the goal lines as shown. Additionally, by introducing the Stigmergy logic for the agents to recognize the opposite agents' trails, the generated goal lines were intervened and fused together both at local and global level. These lines perform better under tension and gravity as they showed very less deformation. By combining all the structural data and movement logic as a global field of vectors is created that the agent used to generate the goal lines. By comparing the results of different lengths, an intuition for finding optimal length to the cross-section was developed. As shown, the iteration in the middle has more balanced and evenly distributed goal lines along the length. The zoomed-in view shows the effect of Stigmergy that creates interconnected lattice of lines that is bundled at the middle and spreads wider on the either ends. The generated goal lines is then relaxed under gravitational and wind forces to select the most stable one. To enable the human walkability on the structure, a hatching technique was developed to densify and enclose some parts of the generated structure. In the zoomed-in part of the previous iteration, different hatching densities was tested to understand the lattice formation at micro-connectivity level, which makes a monomaterial line to a multi-material. In this zoomed-in microscale, the micro-connection between the lines create intricate lattice that densifies the structure in high-stress-prone area. To form a multi-tube goal lines, Detour algorithm is used to find the optimal network path to generate the proxy surface for the system. As a continuation from the Detour network study, we used results of the study to generate line structure that were more dynamic. While the 1-2, 1-3 exit-entry forms generated single-layered structure, the 3-4 and 5-5 entry-exit forms created multi-layered spaces, which established the prospects of generating a multi-layered infrastructural intervention. As a culmination of the whole generative agent-based system, a prototypical site was selected with a high-fidelity point cloud. The primary structure of the building was chosen to pin the anchor points of the goal lines. In an elongated network like this, the walkable area shrinks to very smaller within positions far away from the nearest support. As a system to increase the walkable surface and stability of the structure, pre-tensioning of the structure is introduced, in which parts of the structure is stretched and anchored to create a stable and highly tensile surface. Finally, to thicken the usable zone, after tensioning, a micro-level agent-based system generates lattice connection that is generated based on the vector and anchor point logic of the nearest lines. Depending upon the performance of the lattice, different hatching pattern can be created that will enclose and densify parts of the goal lines that are under higher load.
As the next stage in our project, we conducted material research. We were seeking for a material that can be pliable, elastic, it binds on heat, it is industrially made, and it can be quantified as length of material used. Our material study began by testing two main materials from continuous line deposition. During the experiment on the left, we used a 3D pen as a depositing tool to test TPU, which is an elastic filament material. And in the right experiment, we used hot glue using the glue gun. We concluded that the material more suitable for this scale of experiments was hot glue, as it contains behavioral properties that silkworms has. The first set of experiments we conducted observes the self-organization of the lines through its stickiness, weight, and gravity, as well as the possibilities of constructing a lattice structure by anchoring the lines on different points along the planes. Moving to a longer scale experiment, we observed that due to the gravity and extrusion speed, the lines become too relaxed, making it difficult to control and organize for a lattice formation. In response, we implemented a strategic solution by introducing two supporting lines specifically designed to enhance control over the catenary shape of the primary lines. The research then exploits the need for automation in material deposition, and as it is critical to introduce parameters like extrusion speed, material temperature, and nozzle size for a more precise line deposition through a printing G-code strategy.
Therefore, to strategize the material deposition, we automated the process and employed a robotic arm as a proof of printing control. This includes, as we said, adjusting the many parameters of printing, like speed, extrusion, height, and process of printing, to understand line behavior on a local scale. We built a frame that spans 1.5 meters between two anchor surfaces and automated the line deposition. This experiment is a proof of control over the many printing properties, including speed and extrusion. The same number of lines and same amount of speed and extrusion were employed to the two lattices, which resulted in two separate lattices that are pretty similar. In the second experiment, we decreased the speed and extrusion in the upper lattice, which differentiated its material behavior and resulted in a sagged upper layer that meets the lower one to form a thickened lattice. We can here observe that although the process was automated and it was precise, we have, as a result, an organic set of excess line deposition. Next. Then we built a frame that allows us to experiment with a multitude of anchor points and thus achieve a surface through line deposition. Next. First, the printing was explored as a progressive building strategy. We devised a process of line deposition that starts with laying the first primary structural lines, then reinforce them with a layer of lattice, and then build the lattice in between to form a surface. We can notice how through this layering process a material differentiation was achieved by depositing more material on the main structural lines. Through this set of experiments, we differentiate the speed and extrusion of the structure and thus the sagging and the orientation of the surface. And finally, we experimented with layering through controlling height, by controlling the height and by having a vertically distributed, multiple of vertically distributed anchors, or by literally adding more lines in one place, which results in a differentiated structure where material is optimally added. Also, we experience with many anchor points. And through this compilation, we can visualize the experimentation with a multitude of lattice hatching strategies that can be locally printed.
After having the proof of control, we then look into the machine version at line depositing. Here we have 3 prototype iterations. And the iteration 1 is a cable-driven robot system in a metal frame cube. In this system, which every object has its own coordinates, the 4 stepper motors work simultaneously to control the position of the robot in a 3D space. And by calculating and controlling the distance between their positions, the robot can go everywhere inside the cube space. And with 4 pulling wires, we can also control the tilting of the robot to some extent. By decomposing the robot's trajectory into a collection of points at a range of positions, we can manipulate the robot to perform a variety of different moving behaviors. And when we attach a nozzle to this robot, we can create a cable-driven 3D printer. Here we are using TPU, the soft and stretchy 3D print material, and test the system and also see how the robot cooperates with the line behavior. With the control of the moving speed and anchoring delay, the lines printed drop down to different extents with gravity. As the material continues to accumulate, the robot's movement behavior can also cause breaks in the build-up structure. Therefore, we also developed the system with collision avoidance to ensure the self-organizing of the line itself. We then expanded the system to the 1-to-1 human scale to see material behavior and agent behavior. We made a 2-meter high, 1.2 meter wide frame with the pulling motors equipped with gear system to increase the strength of pulling. And in long print runs, the gravity and the movement of the print head causes the lines to be saggy, but as the printer keeps depositing lines, the tension, suspension, interlocking behavior still shows the self-organizing of the line structure. And it's a very lightweight system. We can develop it into a more adaptive one. So, yeah. So in the last iteration, 4 anchor nodes are equipped with suction cups. The weight of the entire system does not exceed the weight holding capacity of the suction cups. And the print head minimizes the components needed to print the material. And the hot end, stepper motor, control board, power supply, and the material spool are all fixed to a lightweight aluminum tube frame to minimize weight and ensure stable and continuous material extrusion. Here, the control and the printing parts of this print head are on both sides of the frame, separated by a heat sink, and only the temperature of the hot end and the extrusion speed are controlled here. With this advanced suction cup cable printer, we also need to develop it with real-time environmental detecting and real-time structural analysis to make it an autonomous print agent. So we set this suction cable printer system in the burial vault in AA to test. We scan the space into point cloud to give information of where and on what kind of surface the system is suitable to be set up. We measure the dimension of the space and position 4 suction cups on the high windows to set out a space 3 meters long, 2 meters wide, and 2.4 meters high. The setup was very quick and also solid. And with the help of the gear system, the stepper motor can nicely move the print head. The problem of the system setting up is that suction cups have limited types of interfaces to which they can be securely stuck on. They only stick well on smooth and flat surfaces. And to make the system print according to the context, instead of having a certain G-code for printing, we developed the printer with a real-time anchor detecting camera, so it can detect and move to the target anchor point. Then we still use the elastic TPU filament as the printing material and put fishing lines through the space to define a 1 meter by 1 meter, also 1 meter high operating area. Then we set up the printer to draw lines back and forth according to the boundaries. And during this process, the elastic lines anchor with each other to self-organize the tension line structure. And from the down view of this system, we can observe the structure similar to the robotic arm printed line structure. But with cable wires, the printer cannot go beneath the printed structure, so that we cannot provide specific behavior like wrapping. So the strategy of forming a surface or even volume is more based on layering and tensioning from bottom to top.
To equip the agent with a degree of awareness, we devised a real-time system that would allow it to scan, analyze, and adapt its printing process according to its already built structure and its environment. First step is the scanning of this, or if you will, the senses. It is a search for visual information. Then this information is transformed into data that goes through layers of analysis in the brain of the agent. And then a new G-code or a set of printing commands are generated. The agent then adapts to its environment and its own print as a result of the feedback loop between the brain's analysis data from one hand and the scanned print from the other. Then we set up this experiment as a proof of concept that allows us to perform the scanning and analysis behavior. Scanning is achieved through a camera and a Kinect depth sensor that would put the line in a more three-dimensional context. This data is then structurally analyzed and compared with the previous G-code. Here we can see a real-time material deposition that is being, which is an object and color detection by the camera. Then these lines are then translated into a point cloud data. Then the agent is able to analyze this data into lines. It then runs an examination on the displacement of anchors and lines connections. Then it runs a stress analysis to check the structural integrity of its own print. Then it overlaps it with the previous G-code to be able to adjust the next set of G-code according to each area of study that was done. This is a phased process that is performed over time, and we can see how the agent will execute it in real time at equal intervals and is able to adapt its behavior progressively and finally achieve the material behavior and deposition required. The agent then acts autonomously and has a specific field of vision and collision detection radius. Here it shows how it's operating within a specific printing area between two anchor surfaces and is able to assess the line deposition history and then print the next set of lines. The agent doesn't only have self-awareness, but it also is able to perform in collaboration with other agents at proximity from it to build a homogeneous, stable structure. Here we can see both printers laying the main structural lines. The agents then collaboratively build the lattice filling while analyzing their print and the neighboring prints of other agents. This lattice structure is then structurally analyzed by the agents, which dictates the placement and density of further reinforcement of material and layering on the existing lattice.
In our next research phase, we are focusing on introducing tensioning techniques to ensure structural stability and enable workability on our lightweight structure. Through analog line deposition, we were able to develop a practical multi-material printing method for tensioning. By depositing 7 layers of material, starting with a grid structure as the base lattice, we then applied material gradation on the pooling points, preventing the breaking of the structure when it is in tension. Considering that, we used our technique to enable stability and workability, but also as a form-finding technique on how through tensioning surfaces we can create a functional space as well as a spatial experience. For example, by pulling one surface down, the surface transforms into a ramp, while if the surfaces are pulled apart, a semi-enclosed space is formed. Therefore, the tensioning and anchoring determines the form. As we can see from the results of these experiments, after tensioning the lines, one could visually distinguish the lines in compression from the lines in tension, and that contradiction makes the aggregated line organization intelligent and adaptive. Therefore, we started composing more complex morphologies and notating these spaces with different usages. For example, the right model creates a workable tension surface with a covering on top and bottom that translates into a tubular space, while the iteration on the left acts as a spiral tensioning structure that can be used as a transitional space for taking people on different floors. For a more precise exploration of this process, we digitally simulated the printing on different layers, and then by using structural optimization techniques, we were able to get a stress color map for a more optimized material distribution across the lattice surface. We then tensioned the 3 surfaces to create a workable tubular space. Using this technique, we started rationalizing the space into a catalog, looking at how the spaces can vary based on different prototypical scenarios. Therefore, the first catalog looks at how we can create entrances and exits by pulling or pinching the lattices. The second catalog notates iterations that are tubular transitional spaces. However, if they are stretched outwards, the tube transforms into an expanding interactive space, introducing slowness across the experience. Last but not least, the final catalog explores long-span linear iterations that have different distributed routes that people can take to move along the structure. This makes it a multi-layer infrastructure within a tubular tension space. As we have concluded our loop system, we've been identifying urban scenarios to apply our methodology and workflow. Considering megalopolises are characterized by tall buildings and infinite potential anchoring points. We envision the High Line in New York as an excellent example for implementing our system. Taking careful consideration of anchoring points, side linearity, and visual urban connectivity, we've identified a section of the High Line with optimal exposure to structural suitable anchoring positions for our project. Choosing these specific anchoring points, we formulated our structure and subsequently conducted structural optimization based on the load-bearing requirements for walkability. Our generated form seamlessly integrates into the existing urban fabric. One can observe how the site forces, including the heights of the surrounding buildings and strategic anchoring positions, influence both the form and the architecture. Through a playful interaction between established urban structure and our generative adaptive aerial spaces, one could suggest that we have the potential to experience the city in 3 dimensions. This perspective allows us to perceive buildings as objects and explore additional spaces such as rooftops. Elevated architecture has been a fascinating project for architects. This desire to elevate the human experience of the city remained largely unrealized as the space below the bridging normally becomes a compressed space. However, our project, through its translucency and lightness, it is a powerful infrastructure that it is present at the same time absent. Thank you very much. Now we will walk you through our models. So this is the primary research we did. We made some boxes, put some silkworms in to see how they interact with the space, how the collective behavior works, and how they create this line infrastructure, as we call it. And then we extracted these logics and this understanding when we used tape as a proxy material to create these spaces with one line. So we made these experiments having these columns, picking points from these columns, we can generate different kind of spaces. And this is our terrace experiment model. And then we went to use the glue gun and these support lines to weave these spaces in space. And then by tensioning them, we can create different spatial catalogs. And
I'm just showing the suction cable printer here, the nozzle, which is easily to be turned on. Here, I think it's running out of battery maybe. So, you can see the suction cups here. So it's like very easily to attach to a smooth surface with this kind of system. Actually, because the stepper motor here we are using actually for like 3D printers in a very small scale, but we scaled it up like 2 or 3 more times. So we are kind of confident that this kind of system can be used in a more urban context. So we finally have this iteration in this urban context to see how the tensioning structure is going. I think that's all. Thank you.
Congratulations, guys. I think your presentation was not only very interesting, but I really appreciate the level of precision in your research from the initial, setting up of the rules all the way to find a way of, activate more complexity in the system. What is very clear in your project is that from the concept of linearity and being straight, you actually find ways of constructing spaces. And those spaces are not, are of course let's say the addition of a series of segments and lines, but they are actually the final way of representing is a very complex space where from linearity you get to multiple levels and expansion of spaces. I very much appreciate the work done to really go from a simple robot to a robot that is learning throughout. So yes, there is a heavy input at the beginning when scanning the spaces and when essentially, for you to establish how it needs to move. But the level of sophistication comes by adding, let's say, this learning pattern of the machine itself. So the result is, in a way, controlled, but unexpected. That makes it very, very interesting. There is one aspect, though, that I wish you would have told us a little bit more, is essentially by changing the density of this system, you're not only activating different strength of the system, but you're also creating spaces where light transmission is very different. And somehow this, for as much as it's fantastic, the technical aspect that you're trying to achieve and all of the work that you have inputted in the system to make it extremely compelling, there is something about the aftermaths of your own exploration that is to do with the qualities of the spaces. And in particular for me, aside from the structural behavior and elasticity of your system, is about how you read those spaces in relation to different densities as well as different translucency of the space. So I don't know if there is something that you might want to tell us from the initial silkworm all the way to the last final intervention. It seems to me that assessing the project only in terms of the technical and structural behavior, but also in terms of how you move, not on a plane or on an inclined surface, as well as the light effect on the overall final spaces that you have created.
We see the project being more technical and structural analysis based was one of the selection criteria to select what kind of lines, lattice, and network will work. I would say a very nice proof of concept of lightness and translucency and how the space feels was the terrace which we did. We thickened the bottom surface so people can sit and experience it, but the top surface were left open so the light can come through. So the thickening the bottom, and it also transferred to the lattice network, the printing exercise, everything, because the bottom part carries the load. So it was, in a way, making it structural at the same time lightweight. I hope I answered your question.
Well, congratulations. I love the project. I think what's very commendable is how you identify the gap of knowledge with the use of scaffolding and how your project then becomes something that is completely unique, original, and memorable. I just think that at this stage, I would like to hear more from you as to why. Like, why do you think this is important? When should we be spending resources in deploying this kind of architecture? And when you're choosing the Highline, I just want to know a bit more, like, why, like, what is motivating that site? Or, like, when should we be doing this kind of architecture?
The main reason we picked the Highline was the linearity of the space, and also we found it very nicely constructed, where we had these very tall buildings and the potential from picking high points and low points. So the Highline is used as an existing structure to pull down points, and then the buildings next to the Highline to pick high points.
So one of the things that first of all, I appreciate the sort of rigor, development, the sort of like comprehensive quality of the project. I think for me, it's an interesting opportunity to sort of like reflect on how to think about the project within the framework of design research. So you're in the design research lab, you're doing something which is, obviously has architectural aspirations, but it's something slightly different. It is design research, and so. What does that mean exactly? I think there's a lot of different things can fall into that general category, but one kind of design research is domesticating unruly systems into things which can be amenable to human intuition and control, right? It's almost like making the natural industrial in a certain way, and I don't mean industrial pejoratively, but instead something that can be deployed in a systematic and sort of deliberate way. And I think you've done that in sort of, very admirably. There's a few maybe details that might be worth considering. One is that the system that you're in the models, if I'm reading this correctly, that there's a primary structure, which is actually this kind of like fishing wire, and there's a sort of like secondary structure that's sort of that's the printed material. Is that correct? Or yeah. So I think. It might have been an expedient for the models, but I think that's actually something to reflect on. Is there a further hierarchy that you can subject the design to, which makes it in some ways more effective or efficient or even legible as architecture? So if you, for example, were to take the kind of like minimum structure of this thing that you developed with this fishing wire, that's a very particular pared down kind of like elemental intervention. And how could you think about analyzing your process more generally so that you have that elemental structure? That's maybe one material. And then there's maybe a second material that is this more stochastic kind of material, which adds all sorts of very almost like haptic qualities, and it's really beautiful. In terms of kind of like the implementation, I think the robot is amazing. About 15 years ago, there was this really beautiful project that I loved called Hector, which was basically a single sort of like catenary wire at the end of which was suspended a graffiti robot. I always loved that project because it was something that could be that could intervene in a guerrilla way in the context of the city. And you have that same kind of quality. You can bring this into the city and then create these kinds of interventions. Now, this is I think a perfect opportunity to bring in also emerging technologies around machine learning and AI and the classification and anticipation of the deflection and deformation essentially of this material, right? This is a material that's hard to predict. You mentioned the layers of analyses that are necessary to make some sort of adaptive prediction. Instead of sort of building all of those engines to make those predictions possible, you have a data set here, which you've created in the process of scanning continuously, which you can use to actually train a network to do those kinds of anticipatory calculations in a different and maybe more efficient way. So, recently there's been some interesting work on that around sort of like ceramics printing and printing with other stochastic materials. It's super relevant to the kind of things that you guys are doing. Overall, a very, very interesting, I think, example of what we might mean by design research. So, congratulations.
Just want to come in and say something about the methodology and how you present your work. And I feel, first of all, I love the project, and in the final architecture and situation is great. I do, though, feel that, of course, you wanted to stay away from simple available means. For instance, when you some of the simulations, you could have done simply mesh relaxation. You start with the particle springs kind of system to operate, and it's nice. Let's say when Andrew starts to talk about that, the way you actually generated the model, there's a number of moves you're making which are not in the kind of explicit system you're presenting, which kind of afterthoughts. You generate in the end surfaces and you pull them and pinch them and stretch them, and that could be predicted by, so let's say, kind of a particle string system. And somehow I feel when I first saw when you do empirically these beautiful models in Bedford Square, in Regent's Park, and then finally in the terrace, you're just showing a quick flick but there is something about this where when analyzing actually how this is actually produced, how these initial lines hanging, how this is pulled together, actually not quite clear about it. So when you have these empirical models, rather than jumping into a particle string system with a default tube and some kind of squiggly lines which generate something which I think has very little credibility and connection, to actually go through this on what your intuition you have, which you learned, how you lay out these initial lines and know that you would get somewhere. That, I think, is there's this kind of, let's say, I would like to have a better word, but it's a certain dishonesty or somehow, or not truthfulness to the actual processes. And there's a second layer of where you inventing processes which aren't fully delivering. I also thought that I would know more like to more about this robot. Obviously, there's a problem of tensing anything. Can you actually do flat surfaces with it, or is it really these drooping and undulating things? And although in the room up there, it seems that you've been doing surfaces, but you again had to stretch your frame first, and then etc. So I think there's a lot of although there's an enormous sophistication and achievement in all these robots and in a lot of the simulations and ideas, I somehow feel that you haven't been, in this sense, kind of rigorous to the actual processes and empirical emergence, because there's something about this emergence of these forms which isn't somehow not captured in any of the models. It's in that final pulling, but which is in the end then an afterthought. So this initial kind of strange way of having these loose tapes and through the accumulation and the way you do it. I mean, for me, there's a magic in the actual result, which I don't know how to produce. You kind of know it viscerally, but I'm not sure if you know it explicitly and have described it and starting to simulate it, and whether the tool you have can actually reproduce that. That's my question. There's also this kind of strange, these kind of interim stages which are so different from the final, and so you're laying lines where they not end up at all. So that for me is a puzzle and magic of the project, which I haven't fully grasped or reproduced.
Well, layering on to what you're saying, I do agree. First, I wanted to say this is fascinating. You've done such an amazing job, and I love that this is a research lab. So a lot of this is just researching, you could call this some sort of tensile structure with some AI built in it, which is fascinating, by the way. The end result is what looks like my 7-year-old's dream of a playland. And once you guys are old enough to have kids, you'll find yourself in very compromising positions in weird playgrounds that are way too small for me, but I go in there and I'm crawling around and it's amazing. So what I'm saying is no matter what we did with all this research, the end result is a playground. It's a freaking fantastic playground. I want to go into the High Line and crawl around and have fun, even if there is no health and safety, I don't care. So what I think is fascinating, though, is so much of what everyone's doing from a research basis comes from nature, and the nature of snow and igloos, or the nature of penguins, or the nature, here we're looking at caterpillars and worms. And these silkworms are creating this because they have to for survival. They find a way to triangulate between 3 surfaces to create a cocoon so they can turn themselves into a butterfly. And that gives it purpose, where we're doing this to make a playground. So I'm thinking we're in this situation right now where there's a shortage of housing, there's people having babies in the streets. I'm just saying, is there a way where we could AI learn these machines to give it purpose for these strings, and say, find a condition where you've got 3 surfaces, like a caterpillar, where we can cocoon a house to birth a child or something, I think there's a more intelligent result than well, trust me, I think this fantastical playground is a fantastic result. But it's hard to believe that so much intelligence was put in to an AI learn. And the fact, this is why architects are such great generalists, because you freaking computer programmed. You're not even computer programmers. I was in shock. I'm looking at Patrick like, oh my God, these people are geniuses. This is amazing. But the fact that you can program something to make a playground, why can't you program them to make it, something more, like a caterpillar is making a home to metamorphose, for metamorphosis. Can we not do it for something more purposeful?
I think it's superbly purposeful.
It's not the point in the module. The point of the module is that this is a research lab. This is awesome. Okay, now I think the next step after this is now what can we do for like humanity? People in, I'm just going to make this up, like Africa that has no habitation, like, there's another step. There's a bigger picture, but it's an amazing project. Well done.
Can I start? I also want to applaud you for the amazing research. I think I really love the steps you've done to come to the project. It's interesting the steps you went through. One, here you see you're creating space, but then you're deciding to work with a surface and you're pulling it up and create kind of these roofs. So when we worked on 28th Street in New York on the High Line, the client actually asked us to do an installation in front of the building to protect from, like, basically a canopy to protect from stuff falling down, to injuring the people on the High Line. And I think yours would be much better. But what I'm saying is, I think they would be nice because it's such a light structure which you could construct and then take away, which makes a lot of sense. And I think it would be amazing. Like when the last 20 years, all the buildings went up. If you would have put this roof there just to protect the people that they can use the High Line, and this light structure makes totally sense. At the same time, this model I like. Yesterday we talked about office building being, take out the core or the floor slabs, and I wonder if you could implement like a structure, temporary structure to hold the facades. What I'm saying is, like, I think what this system can do is not really full explored. I think there could be much more benefit because it's such a light structure to have for temporary use. And maybe I just encourage you maybe to think more what this could do for the future. But amazing project.
Thank you.
I just wanted to say, based on just the last two comments, you have here in the room people who you could work with and collaborate with. And so where you're at is like, where does this go next? So do you make a playground with Dara or think about someone who's already done something on the High Line? And for me, that is like really a beautiful, like to be in this space, that is a conversation you should be having, is where do you take it? I think that, we all felt like there was so much going on, and congratulations on the robot. We kept gasping, really. Yeah. But and then you have this end thing, and suddenly there's a whole other world of possibilities. And for you guys, that's an opportunity to be inspired and to have ideas with where you've come to with the material and the process and whatever else is there. I think part of this is also just a lesson in storytelling for all of us, right? Where do you start with and where does the story end? Your name at Meta X, I thought of Facebook and Twitter, so how do you consider really conveying what you're trying to say through your work? And if you are using robotics, machine learning, this is a deep research project. How does that come across in terms of where you're taking it? So that it is really about, of course, lending to the future through real R&D, which doesn't happen enough probably with materials, and then to be working with people, through the course of your research. I don't know how, of course you have these amazing people, but just to be inspiring yourselves with somebody who's already worked on the High Line, if that was your idea, and that would be the best next step.
Just super briefly, I think the purposes are superbly important, and it shouldn't be underestimated. I don't think you need something more heavy to burden this. It's actually quite nice that it is an elegant, highly purposeful structure, I think. And I want to throw this in when I was living in Berlin in the 90s and Christo and Jean-Claude wrapped the Reichstag, what this generated, and it was just a kind of space. It wouldn't even kind of be on the surface. It was a love fest for the whole time. And I think I see the Highland has some of that, kind of an urban communication thing, and I can see the surface beautifully with people lodging themselves and hanging out and moving around. And I think that's fantastic. And of course, realistically, the canopy is a no-brainer, would immediately happen and help, but this occupiable surface is also beautiful. I would differentiate perhaps the two surfaces, the lower one maybe slightly more stiff, and it has these moments of, so you can do a lot of develop, but I think, just to contradict Dara on this one, I actually think there's a strong element of this, that this has this kind of public architectural surface, which I think is highly inviting and highly suggestive, communicative, to be on the Highland and actually see that next layer and jumping there and being transparently lodged above. I mean, it's fantastically purposeful.
I totally agree with that, but I agree with that. I think if we're gonna make a beautiful, fun structure in the High Line, I'm gonna hire a designer and I'm gonna hire a structural engineer, right? Because I don't wanna die. But if we're gonna have a machine-learned AI structure builder, this has to have a purpose. It's not a beautiful structure for fun. It's a purpose. So, for example, there are a lot of animals losing their home due to, a global crisis. So is there a machine that can find a surface to build homes for something? Like, give it a purpose. It's not a beautiful structure for fun. It's
how about the lonely New Yorkers?
The lonely New Yorkers, all the homeless people in New York.
It's lonely.
Fine. For people, animals, life, I feel like there's a bigger purpose to a machine-learned web builder. This is like a mechanical spider. There's something so beautiful and purposeful about it that it has to be for more than just a playground. But I love the playground. I'm sold on the playground. I'm going to the playground. And you're right, when Christo did that, it was like, wow, we saw the world in a different way. But you didn't need a machine AI learned designer. You just needed someone with vision and a structural engineer in this case, right? But yeah, it's beautiful. I love it. Oh, yeah.
Okay. Thank you for me too. And I agree with many of the comments as following on the last one about the purpose. I would say that I would actually comment on the project on two levels, because the one is the level of methodology and the process. And I think that was extremely precise, extremely sophisticated. And in one way, that's one objective, I think the main objective of your project, right? To develop a method of thinking, of working, and also to develop a building strategy. So I don't know if I could not read what you have here in a very literal way and say it's a playground or not a playground. I don't know, perhaps it is. But I want to say that it seems to me that you are trying to propose, right, and find a way to foreground and different building strategy. And I think this has a value in itself. And also that what means also to experiment and what means design research. So on the second level, if we look at it as a environment, a material environment, right? Then perhaps I would start from your first statement. You say phenomenon as technology, and I would say that I would reverse that. Perhaps as a kind of approach to material and materiality. And I would say technology as phenomenon, right? And that goes back to your first images, and the first, you are using the cocoon and the silkworm network, and I think that's a very nice reference. And that starts indicating what the purpose might be, because here again we go back to the idea of sheltering and creative more enclosures, right, and environments and multiple interfaces. So that's how I would see it. And if in these terms, what for me perhaps it's a constraint in the way you try to visualize a possible way of implementing the system is the more the frame. There is always a frame. There are buildings, and you attach this floating environment, and then I think these points of attachment or the points of contact for me are extremely important. Also, when I look at your video, because it's there where you start really interacting with the existing, with materials, with buildings, with people, with movements, right, in a different way. It's not just to hang something there, but it's to alter and modify the environment, right, and create perhaps cocoons or enclosures which can be used, can be adapted, can be inhabited, can be appropriated in very different ways. And that's where I see the potential of this project. So thank you for that.
Okay, maybe just to conclude before we go for lunch, I think that this is a really important project to kind of conclude at least the morning session, because I think the issue about what design research is and what's at stake in it, the Samuel Beckett quote that keeps popping up there, fail, fail again, fail better, I think is a really important part, because nothing is so prescriptive and linear where, like, you know, if it was so easy, we just do this, everything kind of works. And I think what's impressive about the project is your ability to continuously try to work through some of the problems. I think you focus maybe a little bit too much on the technical, the line, the analytical, and the question of purpose, I think, is important. But not all designers need to state the purpose of a system. What's kind of really interesting about the conversation is the affordances it gives other people to help you think about possibilities about how this kind of project could offer possibilities to address multiple problems. There is a kind of unsaid kind of statement on my part and in my studio, which is representation, you know, to be honest with you, is the death of architecture in my real feeling about things, because I think at some moment we hold too much accountability towards narrative and representation and ideas without necessarily always proving some kind of commitment to trying to work through the problematics of it. I mean, Patrick brought a certain kind of conversation about the integrity and the honesty of certain things. There is a tendency of looking too much at these models. I think he's right. In some of those early installations that you guys did, there was a lot of knowledge there that didn't easily translate. But I think you need to make sure that people understand that you've been operating in that. The machine vision version is to be able to identify those things through an automated way. The Super Bowl football camera system to be able to think about multiple robots, which is something that also you should state more clearly. The cocooning uses the silkworm's body as a scaffold to make that happen. To develop a system is scalable in the urbanism, you're trying to do it without scaffold. So I think those first comments of Andrew with those primary lines, I think you can, you know, not have to do this all in this kind of like printed floating system. I think it can have different hierarchies. When we start to look at these detour networks, I do think you're a synthetic version of Fray Otto in spirit. And I think that that doesn't necessarily resolve itself in a project. So I think it's a good way to finish this session. We're going to pick up hopefully in a half hour because we're running a bit late. But I think it's really good for the discussion, and thank everybody for the very purposeful conversation. Thanks.